So I'm going to be working on Dabble today. Which is my Airtable clone. But I'm going to start by kind of showing off two neat abstractions that I've been able to put together mostly since last week. And they're two systems that are pretty core to a lot of tractor stuff and have been bugging me for a long time that I don't have like a better abstraction for them. One of them is very general, and just trying to get feedback on it has been difficult because people might not know like what it's good for or whatever. Usually the case. I'll try and explain that. And then the other is actually going to be useful in the Dabble project. So I'll be using that today in Dabble, so hopefully it'll kind of prove itself useful. But then it also simplifies a bunch of stuff in Tractor, so and actually opens up a lot of cool possibilities. And it just ends up really nice and clean, so pretty excited by it. I'm gonna show both of those when we get started in like 5 minutes. wanted to show this. I don't know why it's sort of like both video game nostalgia and 90s nostalgia in one. It's a Sonic the Hedgehog fanny pack. It's not a very big fanny pack, but I don't think you want big fanny packs. It's like that's a fanny pack I would wear. Alright, so like I said, we're gonna work on Dabble, but first I wanted to talk about these two libraries that I made over the last weekend, I guess. And I had to kind of explain them. The first, I mean, it's very generic, and you're like, why would you do this? Maybe I can kind of explain it here. So at the heart of Tractor is this sort of Uber data structure that's not unlike kind of what you get in Unity. In fact, it's basically modeled after Unity. You have a hierarchy of objects, and then those objects, which can contain other objects, can then have components on them, and those components then can have properties and fields or whatever. And you know, one of the nice things is that they're just, in Unity they're just classes, in Tractor they're just structs. And one of the parallels, I mean, there were kind of two parallels with this data structure when thinking about how it could be used. I mean, there's a lot of ways I can use this, and so I'm really hoping pretty quickly get to a point where I can start sharing those. But there's parallels to both the file system and the DOM. Both in that they represent a data structure that has a very sort of like common, well-known API, and so it becomes a sort of foundation for everything else. You know, it's ultimately the API in the browser to show things. On the file system, almost everything, you know, uses the file system, so that's sort of such a common API. And if you look into stuff like Plan 9 or whatever, you have all kinds of mind-expanding ideas. So anyway, I don't have Tractor Studio running right now, so this is an old screenshot. You can kind of see that there's the hierarchy, but the hierarchy then has, you know, every node has components, and those components are structs, which can be arbitrary structs, so they can have their own sort of data structure however they want. And so it's interesting because it's not just sort of nodes, right? Where typically if you have a tree data structure, you have you know, a node, it has a parent and it has children, and then, you know, the children and the parent are both nodes and takes you up and down the tree. In the DOM, because they're sort of modeling XML, which is such a weird format for the one reason of attributes, like the fact that you can have, you know, every element is can have a parent and has children, so it is basically defining a tree structure. But as well as every sort of inner and outer element, every element also has attributes, right? Key value things. And then in the DOM you have a whole lot more, but that's kind of a weird data structure. Like if you were to try and model that in JSON, it's not like a one-to-one mapping to your typical like dictionary and array or list kind of generic structures. You kind of have to make this weird, first of all, it's a tree, so you have to first model a tree, and there's a number of ways you can do that. But then, every node is more than just, also has attributes and all this stuff. So it's kind of complicated. And similarly, this is complicated in that it has that tree structure. And so you're managing, so if you're thinking about the API, you're not just managing the children, but you're also managing the components on there, right? So there's 2 lists that every node has to manage, right? So again, comparing it to the DOM, this is a pretty core API, and so it's one of the older things in Tractor that has already been rewritten a couple of times. And the problem is that the whole API is kind of defined in here with some interfaces, and it's such a complex interface. I tried to break it down into smaller interfaces that sort of roughly, I kind of took the API that I had and just broke it down to interfaces, not necessarily applying sort of the best practices for doing that in Go, but something that works. So for example, we have a tree node interface. So ultimately what we're trying to make here is an object, right? That's the node that you see here and that you would operate with. It's sort of like the DOM element or something, right? Node. So tree node basically includes, all these operations that are for a fairly ergonomic but still very minimal set of operations to work with the tree. And there's a bunch of things here that I would do differently and have done differently now, and I'll kind of show you that in the example. But you might want to get to the root, you might want the parent, set the parent. Sibling index is just its index among the other children. You can change its position by setting the index. You can kind of iterate to the next and previous sibling nodes. You can, of course, get the children, which are other objects. See, already we're sort of like, well, this is a tree node, but we're returning objects, and it's like, that can get weird trying to figure out how to make that work. And that's one of the things that we're trying to resolve with this data structure without having to resort to just having like empty interfaces everywhere, or like trying to rely on generics or whatever. Especially because I've already, looking into the proposal stuff for generics, I'm excited about them, but I'm already surprised by some things. For example, methods you won't have generic methods. And that's relatively easy to say, well, you don't do method. I mean, it has some implications, but for the most part, you'd say, okay, well, now it's just a function that takes the first argument as the receiver, and you should be fine. But still, it's those little kind of surprises that impact API design. Not that I want to take advantage of generics. And in a way, what I'm trying to do is solve the sort of operation orthogonality that you could have in more dynamic languages, or maybe with generics, but using the current Go primitives. And it'll be improved with generics, but I think even with generics, it's still interesting. But we'll get to that. So more about what we have, the API that we're trying to model here. So if you have children, it's a list of children. These are kind of the minimal things. You need to be able to index something from children. And these are because, our slice representation of those children is not like a mutatable thing. So that's why all these operations are here. You want to be able to basically insert at a point, remove at a point, remove by value, and append by value, and kind of do most things from that. So that's tree node, which makes sense. We're modeling a tree, except also we have components. All right. So a tree node will also have a component list. And so now we're doing very similar things. We're sort of managing this list of components that might be on a node. We have to you know, again, append and remove by value. But, you know, you can see here that it was happens enough that it was helpful to have a move at method. So from an ID to a new index, from an index to an index position. And again, insert at, remove at, and like has component, get a component by name, get a slice, right? Pretty typical things for like any kind of list that you might do. And again, this isn't really about, you know, you might think, well, you could do like a generic list with generics, but one, I really want people to limit the use of generics. And if you can't have generic methods, then that means you're not going to be able to use interfaces, and interfaces is the real sort of in good designs is properly utilizing interfaces. And so that's what I'm trying to do here. And then it turns out nodes also have attributes. We have some key value stuff here. So this is basically kind of like a little dictionary. We can get values, set value, delete a value. And so that's, you know, it has its own interface. There's some kind of reflect-based stuff. So given a component, which would be any one of these, right, which is basically a struct, because there's so many dynamic operations here, you want to be able to get kind of look up values in that struct and in that data structure by, you know, some kind of path selector, as well as set the values and call methods. So these are all separate things. I think maybe thinking that, you know, other things might have those separately. Some things might have a getter, a setter, or a caller, or whatever. But then ultimately you have a component interface which puts all of those together. So you have all those. And then we have some other things here like index, which is its position, right, in its list of the component list, being able to change its position. And so it's very similar to what we had up here with like sibling index and set sibling index. These things also have an ID and a key and a name and an icon, like various kind of identifiers. You know, some kind of pointer to its container. You know, what component, what node in the tree does this component belong to? And that's more or less it. So that's a component. And again, you manage components through a component list, which is on a bunch of nodes that you have a tree node. And so finally, we kind of get to being able to do the object, which is a tree node and a component list. And this is part of the reason they're also component getters and setters, because it can kind of delegate those to the components. So you can treat an object like a component in that way. And then you have some kind of similar repeating things here, some identifying things, an icon, a name, an ID, and then some stuff to find things. And again, this is a large interface, and it's because it's sort of an iteration of the previous design, which was basically just a giant struct that has all of these methods on them, and then that would be your API, which, you know, APIs get complicated. The DOM is complicated, but you know, it's only ever going to get more complicated, so you want to start as simple as possible. And so that's basically the API that we're modeling here, and it's interfaces because even though we have kind of concrete or default representations of these things, for example, these are a component represents sort of a struct, and then the tree is something that sort of is persisted and you know, is written to a file or something. It might not always be, or there might be some nodes that aren't written to a file, or there might be components that are sort of dynamically created. And so that's why all of these are interfaces, so that we can kind of, all the tooling that's used to kind of put everything together and show the user interface can use these methods, whether it's, you know, our default implementation or something else, which opens up a lot of possibilities, the magic of interfaces. So again, trying to simplify this, the first thing is there's a lot of operations on here, and this was learned from when they finally added the file system interface, well, package that includes the file system interface. And, you know, you look at things like that I've been using, like a Pharaoh, which is sort of like, you know, a file system abstraction that Go should have. But I'm glad that they waited, because the way they implemented it is smarter, and I've improved in my API design from seeing that. You can see, you know, they created an abstract. You know, the problem here, of course, is like most file system operations are done through like the OS package, which has these, you know, they're module level functions, and so you don't really have any way to sort of mock them out or, you know, create file systems that aren't real file systems. And again, using interfaces, you can do a lot of cool stuff. So a Pharaoh does that. So for example, you could say new OS file system, you get the actual file system that will operate on your local file system. Or you could do a memory map file system in which you get an API to a file system, but it's all just storing to bytes in memory. And it basically mimics all the methods that you would have in the OS package in this interface. And so most of these you can find in OS. But look at all of these. Chmod, chown, right? Create, open, open file, remove, remove all, rename, stat. And on top of that, they're returning files, which again have a lot of, you know, their own kind of methods here. So you've got name, readdir, which is, you know, those are only relevant when the file represents a directory. And of course, all the kind of read write IO stuff that they have. And so on top of that, you know, there's, if you've used like the IO util, Pharaoh has a bunch of utility functions that can be used on top of those. And this is sort of getting at this idea of, you know, why aren't these in the interface up here? Because it doesn't need to be, right? These can operate on those interfaces without being part of them. Ideally, your interfaces are as few methods as possible. And then one of the benefits of that, when we get to the actual Go file system stuff. But so that's the API. It's pretty big, and it took Go a long time to kind of do something official, but this is their file system interface. It just has one method. I was like, what the fuck, right? That's almost exactly the same as, you know, what you had in the HTTP package. So represent a file system for when you want to serve the file system or whatever. It's kind of intentional. Part of it is like because they knew at the time then that that's all they would need to implement the file system that HTTP needs, is just being able to open files. And then that sort of proved the use case of, well, there is the minimal use case of a file system where all you need to do is open files. It's just, you can't do anything else to files, you can just open them, which is the most common thing you want to do with file systems, so it sort of makes sense. So their implementation is just that. But the way to address all the other things that you have to do, and I don't believe that they're actually in here, but you can create extension interfaces. As a simple example, I don't have many, but globfs is a file system with a glob method. So it's basically extending file system to say this is a file system that you can also do glob operations, which, because some file systems actually implement the globbing, so that would kind of make sense. And what's interesting though is that with this method, that's not sort of like what you normally use if you, I mean, you could if you had, but I believe that there's also a glob function. And so the glob function is something that takes any interface, not just a glob, and lets you do a glob. And what it does is it basically does a type assertion saying, okay, I know this is a file system, which means it might be a glob file system. And so it can try and do a type assertion to say, okay, give me your glob, and then it'll just use that glob. But what's nice is then if it isn't a glob, there might be a way it can still achieve a glob, right? A less efficient glob, you know, maybe re-implementing it, which it looks like they might have done here. not sure. But so you start pushing, more methods into functions in the package, a lot like these utility functions, but with the idea that they might overlap with actual methods because of the fact that they're optional, and or you might have sort of another kind of implementation. And that feels, especially somebody coming from languages that really relied on the OOP model, you kind of want everything as a method, any, kind of Ruby or something like that, or which again, more small talk, but every operation that's relevant to this thing should be a method on the thing. Whereas that doesn't necessarily need to be the case, and there's a lot of cases where it makes sense for a lot of different reasons to have both. And this is sort of, Go sort of, their reasoning sort of succinctly brings them all together. Just to kind of expand on that file system example, because I ended up implementing I think, what was the idea here? Oh, because their file system didn't implement everything that a normal file system like a Pharaoh has, then I'm still dependent on a Pharaoh until I have something compatible with file system that has all of these. So I decided to just start doing that, because the Pharaoh is probably not going to push in that direction anytime soon. And I kind of did it as an exercise to experiment with this kind of like interface extension idea. And it is super verbose, like, especially because good interfaces are single method interfaces, right? So you end up with like a ton of interfaces, which means all of those methods are then going to need to have their own functions to kind of do the whole, like, is it a file system with that interface? If not, do whatever your fallback is. And of course, once you have these as extensions, you can kind of bring them together in something, which I did here. I just said, oh, it's a POSIX interface in which I'm able to put all of these things together. And what's nice is you can see how here I sneak this in, which is not a typical thing, but something that I support. And so now we can have file systems, an API for file systems in Tractor that also has watching built in. It's not a separate sort of conceptual package to be using, even though it is behind the scenes. So that's kind of the idea of like using interfaces in a more kind of like composable way, where you break them down and then create extensions, and then you can kind of aggregate those and then try and keep those as minimal as possible so that you can put more functions as functions in the package in the interface. Because one of the benefits to that is because if you're designing an interface, it's designed, like, the point of an interface is to be implemented. So by having the minimal methods that need to be implemented, if you're creating a new implementation, those are the minimal things you'd have to implement. All of these function helper things I won't have to implement creating a new implementation of this thing, because they just work against the interface that I'm implementing. So the minimal interface, and the more things you can push into functions, the better. So you can already, if we went back to the API here, like root, getting the root of something is clearly, of the tree is clearly something that doesn't need to be in here, because all that's going to do is call parent in a loop. And so already, if I were to redesign this, which I have, root would be not be in the tree node interface, just parent. And then root would be a function that operates on tree nodes. And again, as an efficiency, you could have it say, does this tree node implement a root interface or a router or something like that implements root? And if it does, use that, because maybe it knows a better way to do it. But that's totally optional. It can be done later. And then you have this problem of, like, we have a tree node which needs to manage its children, which is a list which pretty much ends up very similar to how you manage the components. And the reason they have different names here is because they're all being mixed together in the same namespace. And so I tried to give them pretty unique names, sometimes putting component in them just to make them a little, to be different from children. So now when you're talking about children, you're talking about children of the node. And then when you're talking about components, you explicitly say component. And for the most part, they're named very similarly, but, a little inconsistent. And they have some methods, like this one has a move, but this one doesn't, right? So we're seeing some patterns here, but it's at the interface level. And so, but they're interfaces for very different things, right? One's for components, one for, and there are a bunch of other things like, a component happens to have a lot of the similar things as an object, in terms of ID and name, even icons. So is there some way to just represent them both while still being able to maintain an API that makes them separate concepts? Like an object is separate from a component because a component can be thought of as this way and it does this, and an object is more of a container and it makes this hierarchy. If I found some abstract data structure that's like they're all the same thing, it becomes a lot harder for people to understand how to use things. You lose the affordances that names have. The names give things to show how you would use them and for what, and to know, this name is associated with doing this kind of thing. This name is associated with this. Even though these very generic, like everything's a node, can be helpful in the implementation from a API and user grok ability, it's a little bit more difficult. But I still feel like there's some common implementation there. But there's one, it's not just the implementation, it's the interfaces. So how do we compose these interfaces? And also hopefully do it in a way where they can kind of work for both component and object, right? So I had this idea, which was started as what I called CDS, which was kind of the idea of, and this ultimately failed, but trying to think about this kind of interface extension approach to designing APIs and look at this problem this way. And I had this idea of like, okay, what if I did create like a very generic interface where it's a node and a node just has an ID, and then start building up some of the pieces of the API, right, that might be similar, like, and I kind of aggregated them just so that I don't have like an explosion of different interfaces. But for example, it's usually pretty common that if you're going to have a value, you're probably also going to have a key. And if you have one or the other, it doesn't matter too much that you also have the other. So the idea that we could have a node, and some nodes can be key value nodes. And then we have a function that would just say, that we can actually use to look them up individually to get the value of a node. We try and convert the node to a key value type assert and get the value. Same with key. We do that for these other things like label and icon. And but the trick is like, okay, but there has to be an implementation, and you're making these interfaces so that the implementations can kind of optionally choose, like, I'm a node but I'm not a key value, but I have like an icon and label or something like that. But then there's also sort of like, well, but you need something, you need an implementation. And it's like, okay, well, I could make one that kind of, initially I was trying to make like, here's a basic node, it just has an ID. And then I would embed a basic node inside a key value node. But the problem with that is that you can't embed, when you do that embedding, you can't like go up the tree to get to something else. So if you make a node and you wrap it in a key value node, and then you wrap it in an icon node, so in the end, in theory, you have all of those methods. If you were working with the key value node, you can't type assert to the icon label node or interface. unless of course the implementation has all of them. That was kind of like, well, feels not, as elegant or perfect or whatever, but it's pragmatic. This is probably what you do. This will just have all of them. And if there's other things like this that, want to be added, they'd have to be done here, or just deal with that trade-off of you won't be able to access some extensions from another extension interface or whatever, if that makes sense. I kind of consider this stuff more advanced Go, like advanced API design Go stuff. So if it's kind of new or it's hard to follow, it's also the first time I've really talked about it. And I was also trying to do this kind of like node option thing where you could configure it by saying like, oh, I want a new node. And you just give it some like with an ID and with a key value and with an icon label, and somehow it would magically all work. Which it didn't when you were wrapping them, but when they're all just the same struct. See, the problem with this is that now these all have to operate on the basic node. They can't just operate on the interfaces because there's too many internal things that we need to mess with. So the idea was that was the core, so that's like an entity, but then any object or component can be a node. And then to create structure, we would basically keep expanding that idea to say, well, it's also a list, right? Or it's also an element in a list. And so you do something like this. In this sort of iteration, in this design, it's interesting because I was trying to do a read-write thing, which is actually pretty helpful. In this list package, there's basically two concepts. There's an element, which is, a value or an object in a list. And then because this package is called list, then there's the container. So it's list container, which is basically the list. And, here's the minimum things for a list. That's kind of like a slice. And then for both of them, I did like this mutable version where it's like, oh, the mutable version is the container, but also lets you do these change operations. That's very interesting. I don't know how useful it will be in practice. I kind of let that go in the next iteration. But same thing, we have to create basic elements now and basic containers, which are very simple, right? A basic container is just going to have a slice of elements. And so this element doesn't have to be a node or whatever. It can just be an element, because in theory, you're given the whole point of interfaces is you're given the minimal interface to achieve what you need to achieve, right? And so in theory, if you have a list, any of the list operations, if they need to operate with an element, it will have everything it needs. So pretty straightforward. And then, of course, the next level is to then make a tree out of this. And so now you're kind of dealing with the multiple layers, right? And how this all works. So I tried breaking down a tree even into smaller things. So even though we have a node here, a node is made up of sibling, child, and parent. And the difference between those is somewhat arbitrary, especially between sibling and child. But the idea is that, okay, a child is going to be a node, but a child is also going to be an element in a list, right? The list of children. But it will have a child will have a method to get its parent. And it looks like I had already gotten rid of sibling here. That's why it's red line. But I was trying to simplify it. The only sibling interface was just next sibling, previous sibling. Just kind of convenient thing to have sometimes, being able to iterate over the from one to the other, like a linked list. And then the mutable child just lets you set the parent, and then parent is just something that has children, lets you index, get children out, and the mutable version of that would let you append, insert, remove, etc. And here you can see how I kind of stubbed out all the other methods from the old manifold API that would be functions now, because they don't necessarily need to be in these interfaces. I can just call them. And so again, this is the importance of trying to do something that works with interfaces as opposed to generics, because it's interfaces that these take. And, you know, I guess you could argue, well, you could do all of these as generic functions with type parameters. But that actually not only makes the design more complicated, but the API more gross and all this stuff. So again, and you lose some of the benefits of interfaces. So trying to do it with interfaces would be really great. The problem is, right, like you want these operations to work on any implementation of, you know, a node. Whether that node is, you know, tree node is sort of some objects, or whether it's like represents components or whatever, it should always be the same. You know, always let you use these operations. Otherwise, you'd have to recreate these operations for all those different types. So this didn't really work out. And this is kind of what it would look like to use. Create a new node with key value. Right, but there are too many problems with like not being able to get at other extensions, and the idea that the core data structure that you're working with is hard-coded to implementing those interfaces. So I kind of in the back of my mind, I thought maybe ECS could help out. Not necessarily the ideas of ECS, but the API of how it's usually implemented. Because even though there's a lot of kind of like things to make an ECS system, at the heart is the idea of an entity. And an entity is just something that maybe has an ID and then contains components. And the more popular Go version, Ngo, which is an actual usable 2D engine in Go, it uses ECS, but it implements it in a strange way, in which when you make an entity, there is no, like, it's a little bit misleading because they call it a basic entity, like there will be this generic entity that you can create for everything, but actually for every entity you have to create a struct, which is not really the way I'd ever thought about entities in my head when I see talks about them. It's usually like entity is just an entity struct, and then it contains, you know, basically a list of these other structs or whatever that are relevant pointers to them. Or, and so here it was sort of hard coding the component structs into a new struct, which might at first glance seem very like Go, but it just doesn't strike me as like the power of ECS. Anyway, it still works in their case. Their API is kind of weird, but ECS is already going to have weird ergonomics. But I found another implementation that was more the way I would think of implementing it. You have a generic entity, and it has an ID, and it has components. And its API is basically just add component, get component, remove component. It has this optimization that's tied into how you would identify a component. So in this case, any component, which can still be a struct, just needs to implement a mask method that returns a unique bit mask. So there's some downsides to this because you have to have, for every component, you have to have a bit mask, a unique bit mask defined for it that this is going to return, which is problematic. But then that gives you the optimization of like being able to, whenever you add something to this, we can do sort of the, I don't know what it is, the and of all of them. And so you can easily check to see if a component is already added without iterating over components. An optimization that's probably a good thing in a high performance environment like games. What this is usually used for, that kind of high performance architecture. But I like this model, and so I thought, well, maybe I could kind of do something with this and actually use this part of ECS, but ignore all the systems and even the idea that a component necessarily has to be data only, because now that would make you miss out on all the benefits of interfaces. So because it's similar but different, and because of the fact that I already have components in my system, and I want every concept in the system to have some kind of unique name so that you're not like, well, is it the blah component or this component? I gave it a name that was a little bit more descriptive of what I thought, which was facets. So this initial attempt here was called a composable data structure, because it's kind of the idea of like, okay, you can start with a node and then turn that node into a list, and then you can turn that list into a tree, and and then you could do any other types of structures that have their own kind of unique methods, but they'd be made to be composed from each other, right? So the faceted data structure, I'm pretty happy with it, and I'm almost like this is too good. So first of all, instead of a component before, an ECS component is now a facet, which is still, it's just a struct, but it also still has to implement a mask, which is a unique ID. It's not actually used in a bitwise mask, or maybe it is. No, it's not. It's actually a unique ID, because that way we can just have a kind of an iterator function that will give us a new unique ID. And so for every new facet we make, we can just say mask is going to return next facet ID, or set next facet ID and a variable in the package, and then have the method return the package level thing. So it's always the same to identify that facet. And then same thing, the entity is just a list of facets and an ID. I don't believe that this is actually used now that it's not really a mask, so I'll probably change that. It's more of just ID or something. And that's it. That's the core of what a entity is. But then kind of combining that with CDS ideas, here's the key value stuff. So key and value are now their own separate facets. Here we're setting up, getting their IDs that'll be returned by mask. And so there's kind of a pattern here in this facet system where not only do you have, and some of this will go away with generics, namely this mask stuff, you have facet key, which is the key that's doesn't need to be public, to be honest, but it's what mask is going to return to identify it. Then you actually have the key facet, so it's about a key, so it's a key facet always the second word. In the mask, it's always the first word. And so you have that. And then you have an accessor function that kind of acts like the utility functions that I've been talking about so far that would take, a generic file system and then type assert, can it glob? Then we'll use its glob, otherwise we'll implement a glob. So it kind of is structured like that, where you say key, which takes an entity, any entity, and we'll try and get the facet key, or the key facet using the facet key. And if it doesn't have it, we'll just return nothing or some default. Otherwise, we'll just return the value of that key facet that's hanging onto that entity. Same with value. It's the exact same thing. And so those are just simple values. Is you create new values and create accessors for them. And so again, what's cool about this is you can create an entity. Some of them have values, some of them don't. Some of them have keys, some of them don't. But the things that we build in here become convention, right? It's basically defining an API that we're going to build on. So anytime an entity has a value, we'll use the value asset facet. And there's a couple of uses for key. This is actually best shown, probably the rest, in this demo that I put on a gist. So this is kind of the API of how it's used in introducing the kind of how you're building up to these different data structures that are then orthogonal and can kind of be using the same operations on each other. So creating an entity is just giving it something with an ID. I was a little surprised as well that the other entity system used a string for the ID, because often it's just some kind of number. In my case, that's actually what I want, because I have a kind of UUID that I use. But if you wanted a numeric ID, I just created a helper that gives you the pointer value. And you can use that as an ID. You need a numeric ID. I don't know that I'll actually use that, but I put it in there just for completeness. So the next step is we'll create an entity, and from here on we'll not give it an ID, so it'll just be an empty string. A new entity, and then we just can give it some facets. And so we give it a value facet we saw earlier with a value of 321. So now we can say FDS value given that entity, and we get 321. So then we want to build some structure here. So we'll create a new entity, but as a list facet, and a list facet doesn't need anything to be instantiated. It's just there. But you usually want to operate with the list facet. So to get the API from an entity, right, you can't just say entity and then use the list facet. You'd have to look it up. And so that's where those helpers come in. This is supposed to be facet list. So this gives you a list that then has the list operations, which, by the way, I guess it's worth looking at here. The list facet is implementing the list interface. And so that's kind of a key thing here, is you could have other facets that implement the list interface. And then all of these helpers, I guess they're in util, all of these things like move, remove, index of, next, previous, can work on those facets because they're implementing the API. They don't have to be a list facet, and we'll kind of see that. But just as a default here, there's the list facet that we make here, and we create a new entity that's a value. We'll call it a value entity, and then we can just append it to our list. We can append another one to the list. And now on that list, we can say, like, show me how many there are. There's 2. We can get a slice representation of that gives us all those entities. We can call value on them, and we can see 1 and 2. So now we can do a couple of extra things. Same thing, we'll create a list entity and get the API for that, get the facet. And then we create a bunch of entities that have values, but they also have keys. So we're creating key value entities. and we're putting them in that list. And now that list is an ordered dictionary, and we can do our slice, and we can see a key and a value for each one. We even have a dictionary package that has a value function that will look up the value for a given key, and it's just using that convention of it's a list, and they're going to have key facets and value facets. And so we can now treat this entity as a dictionary, or do dictionary operations. But even though we treat it as a dictionary, it's still a list, and so we can do this list operation, and we can move, reorder these elements. So you're starting to see how these things are kind of, you're able to use these functions or do these operations on a generic entity while working with interfaces, if that makes sense. This is going way longer than I thought it would, but I'm glad it's being talked about, because I haven't really seen this before. I mean, you hardly see ECS now, so this is very interesting. Even this, it's such a simple idea, and it is a little bit more verbose than if you were to do like specific implementations. But the idea is, over time, as you build up structure, you're gonna have to watch. There's a lot of introduction. I can't really drop into explaining what this is, but hello, welcome, Lunan. Talking about this faceted data structure package, which I think is a really cool thing. I mean, I was just saying it's a little bit more verbose than if you were to kind of do things, but you're able to get a lot more, I want to say polymorphism, but most people think of object-oriented when I say polymorphism, which is why I always have to say interface-based polymorphism, right? Even though we're creating a tree structure here, we're able to use the list operations to move around the children on that, right? And so that's, the idea of the benefit of what we're trying to do here is these composable, faceted data structures that can become more things by implementing certain interfaces, which then opens up lots of operations that can operate on them and across facets that implement that interface. So again, showing this tree structure, even though so we create a root entity that has a node facet, and a node facet for the most part is basically, or rather a node facet implements the node interface, which gives us a pointer to the entity, also access to the key because we use that sometimes, and then parent, set parent, and then children, which you'll notice returns a list. So by interface, not implementation. And so because of that, now we can create some entities that are key value entities, and we can append them to this root node by saying children append. So we're using this list method for the children of this tree. So we've composed these data structures, and we can still use the list operations on those children. So we can sort children on this tree using this list operation. So hopefully you're seeing where the dry kind of interface stuff, and it's not just for dry. Like, I'm not like a super proponent of dry. I usually am first to push away from over drying, as someone who has done a lot of that kind of thing. But in this case, we're getting so many more benefits than just not having to re-implement that. We're making it easier to create new implementations of interfaces, which opens up a lot of cool things. It's just a rule of generativity. If you do things this way, cool things will be possible. And then, yeah, same thing. We're just kind of outputting it. Same as before. We can see that we moved one of these to be a parent of another one. So it's not 3 at the root, it's 2, and then one of them attached to that. And you can see our dict value still works on children. So our children can act as a dictionary if we want to, if they're set up that way. And then lastly, an example of doing a custom facet. So if we wanted to make custom facet, by convention, we would do this and this, which is, and this. Actually, all of this would go away. Once generics are in Go, the only thing you'd have to do to make a new facet is define a struct. Because the entity get, that would have to become a function, but it would be a generic get where you just say get, and we'd probably call it facet at that point. But facet, and using square brackets for various reasons, and we want to get, what is it, custom facet. Oh, and then we give it the entity. And so that would give us a custom facet. I mean, it might actually be like, we might have to do that, but, and then we wouldn't have to do any type assertion or anything like that, which also means we wouldn't have to create the getter. So by convention, we say, oh, it's custom facet. We make it a facet by implementing an interface that gives it a unique ID. And then by convention, we also create a function called facet custom. It's kind of reversing the names, that takes an entity and will give you a pointer to the facet, in which case it's calling get for you and then doing the type assertion for you. So again, all of that can go away when there's generics. But then again, you can do everything that we were doing before. We can create a list entity. And in this case, all of these lists, they have a key as well as our custom facet and its values. And we can even use, because we've got those keys, we can use dict get to look up our custom facet values. We just wrap that in our thing there, and we can get the values that we're interested in. Okay. So it's like taking ECS, cutting down to entities, and then kind of bending the rules, right? Because in all of these cases, the point is actually to implement methods and put logic on them, but you don't have to, right? Key and value are just data facets. So anyway, that would then become the internal implementation for the manifold API. And so it allows me, instead of people having to use all of that API, there would be a nicer API on top where it's like you have objects and you have components, and it might end up being a big API. It would be broken down a little bit, but at least there would be more consistency across them semantically, right? It's like, that ID is always going to get you the same kind of ID, and that's the ID space, and something with a key is, going to be able to look up by that. And so they'll have semantic meaning across, the different things. But again, you also get reduction of API. Like, we don't have to have one API implementing a lot of methods to operate on a list of a particular type, and then have a lot of those same methods implementing on a different type of list, while still being able to use interfaces. Just want to repeat the whole, you could solve that with generics, but that is a very different way to go, with different trade-offs. It's sort of the first thing you'd think of if you're like, oh, we have generics now, but I know better. You want to use generics as little as possible. And then you lose the interface stuff, especially since you can't have type methods, type parameters on methods. And I don't know that Go ever will get that because it really doesn't need it. Okay, so that was the first thing that I was excited about. The next thing I was excited about that I sort of finally did a good abstraction for over the weekend was, so the way this interface is generated is actually dynamically through reflection, but in a way that sort of, has intelligence that, live updates, that's a Boolean, so we're going to use a checkbox, right? Set that up. Being able to, you kind of have to deal with certain things when you're dealing with pointers to other things and how that ties into all this other stuff. But basically there's this idea that components are made up of fields, and that this field system is generic enough that you could use it for really any kind of forms to represent form, field values, key value kind of things. And when we get into our clone, this is not the clone, this is Airtable, but looking at what they do for certain things, like this is the one that we'll be talking about. If we make a new field here, we get to pick a name, and then we get to pick a type, and then depending on the type, we have some options that we can change. And so, it'd be nice if these options just mapped to data in a struct, because that's one of my secret weapons is in design, is just trying to align things as much as possible so you don't have to do these extra layers of translation, because then you have extra cruft, extra boilerplate that you have to write. Right, I guess my best example in talking about that idea is how it's silly that we will create, when we think of microservices, we think of pretty simple kind of functions or little, operations that you can do, but then we expose them over HTTP using REST. But REST is made for a totally different context that semantically puts what you're trying to expose through a totally different lens, because here you're saying it's a function and here you're saying it's a resource. And so you sort of, with a resource, your only verbs are CRUD, and any verb that is not one of those you have to create a resource for. For example, if you wanted to shut down a server in the cloud, you don't want to delete it, you just want to shut it down. Well, you'd have the restful way, most restful way, would be to create a shutdown resource, and you would post shutdown, to that resource, which has a lot of implications. And I described it as like nounifying verbs, because you're taking functions which are designed around verbs, right? Like best practices for naming functions is usually start it with a verb, because it's an action, it's a process, it's going to do something. And then REST is saying, okay, all of that, we're going to change how we think about it and say, now it's all going to be nouns. So now you're going to say this is a resource, it's a droplet or a server or whatever, and anything that isn't get, put, post, delete, we're going to nounify as resources. So you have to do all this boilerplate to define what that REST API is for this function, which is why I'm a proponent of using RPC over REST APIs whenever it makes sense. In my cases, almost all the time now. But because it's literally just exporting the same definition, which means the schema And documentation for that RPC method can be the exact same as whatever that function or method is. And so you're able to leverage things like reflection to basically automatically get, not just the RPC method exposed, but even having documentation and schema for it. And that wouldn't be possible if those weren't aligned. And the problem is that REST models things in a way that is not aligned with the way you model things in code, which is functions. What we're trying to export, usually functions or processes or whatever you want, however you want to think of them. So again, in this case, it would be great if this form actually just mapped directly to a struct. And I didn't have to and so that even if I want to customize it, like out of the box, it'll do the right thing. And that's what you see here is, even though you can customize these component panels, out of the box is just kind of reflecting on the struct and giving you something that makes sense and is usable. So that same system, right, to create these component panels, be the same system, or at least the concept of kind of reflection and types, right? There's really what this is really about is data types, right? You're saying what kind of field this is, which is a certain data type, which is going to have a certain kind of UI component, which is going to be different, but for each field, but you still have this model of fields where they have a key and a value, but then you have complex stuff where you embed, maybe you have a field that is actually a struct itself, so it's like a form within a form, all kinds of things like that. And so, the system that I had for this was pretty good, I guess, in that it worked, but it was pretty complicated, and I've been doing reflection stuff for a long time. Finally is kind of feeling like I can do things simply and straightforwardly now, but basically our front end is dealing with fields like this. So for any component, we're actually just getting a list of fields. And so from that list of fields, we have a type, which is just a name that I came up with for the common stuff like string and Boolean and number maybe. Compound types would use subtype. If it's a struct, then maybe what is the struct type? Or if it's a slice, what is it a slice of? Or it's a map, that kind of stuff. And then there are some other things, like sometimes they're hidden. You have the field name, which is sort of the identifier before it, but that's not always there because sometimes you have a field without a label. There's some stuff that's specific to sort of the context in which this is, in which you can actually address it by path, as well as it having a value, right? Because if you're going to use this data structure to show it, you need to show the actual value in the component, so it needs the value. And then a couple of other things that are helpful for different types. Whenever there's an enum, right, you're going to get a drop down. And when there's a min and a max, that's useful when doing a range or something like that, which applies to numeric values. And then again, if it's a composite data type, it's going to have subfields, and you kind of repeat this. And this is, again, made to just basically be pointed at any struct that we call a component, and it'll create those. So this is the implementation, and I don't know how I, kind of hacking around and finally getting something that kind of works. And it's like I've got this type builder thing where it's a bunch of functions, and this was so that I could do kind of a generic reflection, crawl the data structure, and then for every one, once I figure out what the type is, then I can throw it through these type builders, and it'll kind of set up those field values the way I would, and do stuff like, oh, it's numeric, let's check if it is an enumber, because if it is an enumber, then we can set the min and max, that kind of stuff. you have the complex types. Like this is a kind of complex system, not just for dealing with the reflection, but just kind of, again, like these names correlate with front end UI representations and stuff. But I had a feeling that this general idea of fields, like if you could just model this, that's a really powerful thing. And it has a lot to do with what your data types are, right? Because you're defining all these different data types, and then you're defining for different data types, you know, different things that are relevant to how you display a field, which is a very generic thing. Anyway, I mean, look at this mess. And then, you know, from component, and we have to do kind of a nested, you know, I don't even know what I mean by collection subtype anymore. I mean, I guess it's a subtype that's a collection, so it does something different here, but it also does something with references, because that's, so it's just not a very clean thing. And we've got pointers to, you know, the reflected values of things and the reflected types of things, and we have to have references to the parent because of tree stuff. So kind of simplifying, decoupling things, and trying to solve the same problem, basically saying, okay, I want that, and I want that for our clone, for Airtable, right? I want to be able to say, here's a bunch of types, and those types can have user configurable parameters that will actually change how they operate. It's sort of extra metadata around that value, which is configurable by the user in this case, and would be in Tractor as well, but normally it's just you define a struct and you get that. But and then of course there's other things like, then you have different string representations, right? Almost every value has some kind of string representation because you're going to show it as a string, usually at some point, or over the wire. So, you know, but that's tied into the configuration because of formatting. If you were to do like a date, for example, you can format it in different ways, and so that ties into its string representation. And so, you know, I ended up kind of making a list of, in fact, do I have this list? It might be kind of cool to show. Basically, these are all the string types that Tractor kind of right now supports. Here are some other sort of ideas that I had seen around. And then also Airtable seems like a good reference, sort of as sort of like a, you know, what is the common everyday user need in terms of types? I figure Airtable is a good place to look for that. So you get a lot of stuff that's not particularly interesting from a type standpoint, but from a user concept and you know, validation and stuff like that. It's like, yeah, this is a %. It's going to be formatted differently, just like currency. It's going to be formatted differently. You think of it as currency as opposed to just a number. Some other silly stuff like ratings. I looked at Q because Q also has a pretty slightly more complex than JSON data model. For example, it supports byte slices. I think it might call them blobs. I'm not sure. But blobs is another name for them. I decided to throw in there. So looking at all of those, and then you kind of have to break them down into, then there's sort of all the features, right? Like enums. Which types use enums? There's some up here that kind of map to multiple things, like a number can be an int or a float, you know, kind of like a JavaScript numeric. There's some where the name is more or less just another type. It's kind of in memory, it's ultimately just a string, right? So there's all these patterns. There's, you know, these are all what you'd call basic types. And then of course you have your composite types, which are structures like structs, maps, arrays, anything else that's kind of a structure. But of course you have these other cases too, where you have like, it's a date, which is a basic type, but in memory, it's actually a struct, right? So just trying to get a handle of what everything is. and all the other things that I'm modeling in the field system, like formatting, what, component or representation does it have in the UI? Does it deal with subtypes, composite types? Does it have a default value or maybe even a placeholder value? How do you deal with serialization? What, type will be used to serialize it? Things like, is it a required field? Is it read-only? Is it a hidden field? The range stuff, min-max. Formulas I kind of threw in there because that's a thing here, but it's not really that's more specific to a kind of a spreadsheet type of thing. Of course, everything has a string. And these are just kind of ideas or functions or like cross-cutting concerns. Validation and parsing, what the type is in memory. I actually made a spreadsheet. I didn't make an Airtable, but I made a spreadsheet trying to make sense of all these types. I did this sort of like basic types that you'd have modeled in Go as their types, as themselves. And I tried to do all the kind of basic types up front. Then you have these ones that are kind of like aliases, where it's like, okay, a number, that might actually be numeric, but for now it's just kind of an alias to an int. I want to throw decimal in there because it's kind of a big deal. Floats aren't necessarily great for decimal values. And then sort of thinking in terms of names and how they're exposed to the user. Text is going to be more familiar than string to the average person, so you create a text type, it's just an alias to a string. But then you also have a long text type, which is also an alias to a string, but it's going to have not only a separate name, but extra options and different validation. Checkbox is sort of like the layman's bool. Password is interesting because it is just text, but we just happen to know that it's a password, so we use a password input field and try not to show it in certain cases. Percent's just a number, and most of these are just, formatted text. You have some that's a little like currency, is it number or decimal? Then you get into confusing, so I was like, okay, maybe the alias are cast to these, so they're kind of like referencing themselves. Then you have the type that's actually used in memory. For the ones that blank, it's whatever it's pointing to. Serialized most of the time ends up being what it is in memory, just through JSON. But it's interesting here because, for example, datetime, even though it's a basic type, its memory type is a struct, but we serialize it as a string. Duration is just kind of a type based on an int, so it kind of is another interesting one. Color, I don't know, the best way to represent that in code yet, but it will probably have some custom type, but still be stored as a string. And then select is weird because it's kind of just a fancy input. Then you have references, which are really weird in a special case, so I kind of ignore them for now. Then you have your built-in composite types, and then some other kind of composite types that are, multi-select often is basically a slice of strings. Of course, we'd store it as an array or a list or whatever in JSON. Checkboxes is very similar. That's a type in Tractor. A vector 3, like in Unity or something, where you have X, Y, Z, that would probably be a vector or something like that, and we'd store it as a struct. Attachments, which is an example of something that you can have in here, is probably a I don't know. These are just composite types and more complicated. And then kind of looking at some of the features and just thinking through them one by one. The parse one was pretty common. And again, there's usually a string representation, at least for all the basic types. And that's kind of a pattern that I noticed I didn't really think about, but exists. Like, there's always a string representation of your basic types, but not of composite types. So there's a parse that takes a string that will convert it to whatever type, and we already have those in the standard library for things like integers and, and floats and string conversion package and stuff like that. But it's going to be in different places for different things. But most of the time it exists, even usually uses the same API. And kind of a corollary to that is format, which is you then want a string representation of some value. And I really liked how it worked out because, I mean, I guess you'll see. Enum was basically going through all the ones that would where it would make sense for it to be to have an optional enum. Almost all of them, because you kind of use enum as a way to do a drop down or something like that. So even a blob, which is just a byte slice, maybe you're choosing between 3 byte slices, and so it would have an enum. So most things can have an enum, even numbers. But numbers, numeric ones, are the only ones that have a range. And I think I ended up even saying floats don't have a range, but integers do, and things like integers, or that are based on integers, have a range, which means there's a min and a max and a step, and all of those are optional, but having that as a concern. And then you have like required and read only, and I noticed things like, oh, those are really dependent. Those like required and read only aren't really a concept for type, but how a type would be used in context in a set of fields, right? Same with whether it's hidden or not. And some other notes, just trying to work it out in my head. Start sketching, this idea of like there's a field type interface maybe, and I know that I'm going to want some reflection on it. Maybe I want to know if it's a basic type or not. The methods that made sense for if it is a basic type, you'd have that parse and format, as well as enum and range, which are optional things, and a default value. And then, but then it's weird because a lot of the time I'm talking about a field type, but I'm also talking about a field. And that terminology is really interesting, but I think I'm happy with how I modeled it with that ambiguity. I guess you'll see in a minute, but in the same way that like you call these columns fields, so is the field the type, or are you saying that these are fields? Every row, every record has a field called notes. It's kind of both, right? If this were a struct, a field on a struct would be a particular field, key, whatever, right? And that's kind of what these are to these records. But it's also a type. So it's sort of like, it's one of those cases where the value and the type are ambiguous, and maybe that's okay to kind of treat them as the same. Anyway, you'll kind of see what I mean when I get to the code. But this is kind of what happened. I needed a type for range. You can see why I'm not using it for floats, because I'd have to have 2 different types for floats and ints if that was going to be really useful. And this was interesting. So this package is called field, right? So field type, which is really just saying a type name, which is in theory a user displayable name that represents the type that we're talking about, the type of this field. And we also have a pointer to get the reflect type, which is useful for doing any kind of reflection stuff. Just having it there is really nice. It makes sense to have that for the type and getting the type, reflect type. Okay. And instead of saying whether it's basic or not, I actually just did 2 interface extensions. So a basic type is a type. So we're embedding these. So we're saying we're going to have all these methods and these. We have parse and format and enum and range and default. And a composite type doesn't have any of those, but it does have basically more fields. And so a field is actually both a field type, because in the case of what we're end up doing in the UI, we need the type information with every value. And you could optimize this and, you know, do something in the Airtable case, but still, so a field has a name, and so that's the field name. The type name, which is going to be text, and you have the field name, which is actually the column name, right? This is text, but the field's name is hello or whatever. Now the field's name is hi. Its type name is still single line text, which is different from value, which it doesn't have. But if you were to model this as a field, it would have a value, in the same way that this live updates checkbox, that whole row is a field. You need to know the type. So we can do a checkbox. We need to know its name, so we can say live updates. And we need its value, so we know what's in the checkbox. This started working out and mapping pretty well. So we say a field. But actually, we have, and again, this is the package's field. So the type, the interface field value, kind of using the redundancy of package name. You know, I love that, how you name packages and try and avoid the redundancy in the names. Field is the exception, but you always usually have that exception here and there. So it's interesting that a field, if you just say field, you might be talking about a field type with a name and some other options. It might be a field with a value, but if we needed that, we could say field value, or type assert this field into a field value. In which case we get the value, which is a reflect value, which is always what I end up wanting. And this actually makes the API really nice. So those are the interfaces and a struct. And then there's basically the way I imagined it was I started doing this. I'd say, oh, okay, so we're going to have an integer. So we want to model an integer type that can be used as a field. We implement integer. It implements all of those things, right? It can be used as a value. So if it has a value, that it would have a value. But it could also be used as a type. If we were to just create an integer empty struct, it would be a valid field type. It would have type name, and we'd be able to reflect and get the type. We can get this information. What's the default value? Is there an enum? Is there a range? And we could parse strings into its value, and we could format the value out as a string. What's really cool is as a struct now, we can actually put some of those parameters that we're talking about, right? Like if we wanted to, like I said, model this where I'm customizing this type. This is a type information. I'm gonna pick, you know, long text. Let's do a number, right? Look at all this configuration. We have a default value here. We'll say the default is 2. We also have formatting stuff. In this case, we're sort of picking maybe a subtype. Is this a decimal or an integer? What is its precision? Allow negative, right? Those are all things that we can put some equivalent in this struct and have these methods behave differently given that. And so including the parse and format, right? So you can put formatting data in here, you know, how the user would format it, and then just show that struct as the way to define. It's, I don't know, it's cool. It just all sort of lines up from all these different uses. So you have integer, you have string. You have compound types, like here's a slice. Doesn't actually do anything. Oh, there's this other, because field info, so there is this sort of like metadata / optional metadata that if you're talking about a type or a field, or a field type, you might want, for example, its name. You might want to know if it's hidden, so maybe it doesn't show up in this component panel. Maybe it's read-only. There's a couple of common things, right, that are even common because you see them as attributes on input tags in HTML. So there's a couple of those. And in fact, I turned those into, because most of them are like Boolean. So I actually used a bitwise mask, kind of inspired by seeing it in the other API, but this way. And then also we have a struct called field info that has that name and then more or less a list of flags as a single value. And we can create those with field info, which will give us a field info. So it gives us a nice way to just list out a bunch of flags and a name, and it'll give us field info, which is convenient because what we're doing for all of these is for every type, we're saying float from. So if we wanted to create a new float instance from a float value, for example, we'd use float from because it knows that that's the value it's going to store. So we're going to take a float value. And then we'll also always take a field info, which can either be an empty field info, or we can call with field info. Right? It looks like this. You can do an empty text from hello world with an empty field info. So we don't care that it has a name. We don't care about required or whatever because it's not in a context. So that's empty. But we do have the value that we can get, right? This is a reflect value, so we can say string. All right, I was thinking, what if I had to do all of those methods like you normally have to do? But because we're, anytime you deal with like a single value representation of multiple types in Go, you often create those kind of getters for every type, like string, int, bool. But because we have the reflect value, we kind of get those already there. So that's kind of an elegant thing. Of course, its type name is text, even though it's string behind the scenes. Integer, same thing. Here's an example. Here's just kind of working with field info, so making like a field info called foobar that has hidden and read only, and just checking that it has those. And then we use that with a string. And then we create, because Boolean or bitwise mask flags is kind of a awkward API for some people that don't necessarily think about how that's implemented. We've got convenient helpers here for each of those, so you can say hidden, read only, required, and it just takes a field and it's going to look those up. So if we run our tests here, what I actually did was, so for most of these, you take a value, but for struct, basically I was thinking, well, we need to reflect on actual values in Go, which is what a lot of the old field implementation was doing. All this mess was kind of traversing data structures in Go with reflection, and then depending on what kind of data it is, we'll return, a type name and do certain things to it, right? It's like this was just asking for a better treatment. So this ended up being what it is, like a struct, because in that case we're basically calling a struct. So just this is how we implement struct from. It's just a little bit more complicated than a basic value, but we can take an arbitrary value in here, assume it's a struct, get some reflection to basically get a list of fields from it, and then we start building our list of subfields based on the fields from that struct. And so the fields from the struct is basically saying, the name is already what we want in field info. We can use struct tags as a way to add those flags, read only, hidden, etc. It's extensible, so you create new flags. And then basically doing a switch, reflecting on the value for that field. And if it's an integer value, then we'll store it, then we'll return a field using integer from. If it's a float, we use float from. So it all just kind of fits together really nicely, and I love how that feels. Still have to do maps. Still not sure about slices, and then arrays are interesting, but for the most part here it works to the point where we can kind of do what we were talking about. If we wanted to expose this decimal type as, you know, some form values, right? We wanted to generate a UI in order to do something, you know, like this. It could be generated from the struct and directly mapped to the data on the struct. And we could actually use this system to do that, which is what this last test, not really a test, this is more just like trying it out, but I printed out struct from and then an empty decimal with empty field info. And then just looking at its fields, you can see we have, basically it's reflecting on that struct, right? The public exported names are field info, which is going to have a name and all your flags. And then you have default decimal, which is, you know, because there's a function, a method called default, this couldn't be default, but it's just convenient that, oh, we can put the name. I actually got that idea from this, from Airtable's UI. For almost anything with a default text, default number. So it's like, oh, well, if that's what I'm going to put in the UI, we can just name it that, and then it gives it a unique name. So that's convenient. Default decimal, precision, you know, which would be represented something like this. It wouldn't automatically be represented like this necessarily, but you know, that's just a little cleanup to the generated form. But you can see that we get those field values here, so you can see how it just kind of work if we use this in Dabble, which is what I was hoping to do today, but it's already 4:30 and I've been talking this whole time, which I guess I'm excited because I like both FDS and field, but they're so generic, so abstract, and so both specific to my use case, but also very general when used through my use case, that I'm just really excited about them and how clean they are and how everything kind of came together. Just really happy with them. So I guess that's what this stream is focusing on, is all that. So yeah, bringing this into Dabble. These are actually in a hack package in Tractor, so I might just copy this out into the Dabble project, wherever it is. And, you know, it was on my list to figure out how to do types, and I kind of sketched out something, right? This was my loose attempt at thinking about this from the Dabble use case for it, which is, you know, a table's gonna have a schema, which is basically just a list of fields, and a field is going to have a name and a type name, and then we needed to define all those types, right? It's got URL and email and all of that, so those have to be represented somehow. And so I figured, oh, well, those could right, there could be a field type interface, and then I could create implementations, and all I have to do is implement name and format and parse, and that would be good. So that sort of built the foundation too for how fields ended up being. But this is, you know, a sketch version of like, oh, if there's a text type, it would return, here's the name, single line text, that's what you could show in the UI. Format and parse doesn't do anything with strings, but you can kind of see how we can drop in fields in here. and basically have a bunch of types ready to go. We'd have blobs, we'll have floats, we'll have integers, numbers, which are integers right now. We'd have slices that don't work, but we have strings. We'd have structs, which I don't think Dabble would really use, although we'll see. Time, URL, tried some more things with a struct. See how both of these, like, URL parse is same API, just parse with a string. Format for a lot of these is just calling stringer. Although some of them have parameters you might want, you could put those parameters in the type struct. So for example, not just decimal, string fict, here's the precision from there. But I think date, I think I did that. Oh, time. So I had to pick some defaults here. There's a layout string, and by default, when you give it a time, that layout's going to get set to, I don't know why they don't have the ISO RFC that JavaScript uses, but this is kind of the closest thing that I would use that's built in. I don't know that it's actually going to be this, but I picked, this for this. So by default, that's the layout. And, it's questionable whether this would also affect parse. So you could create this type, set its layout, and then do parse and format. Notice they're the same names, right? String conversion as well, I think, uses the same thing. Oh, well, that's A to I and I to A is kind of a historical thing, but let's try like a float. Parse is parse float, format is format float. So to me, that's the kind of aesthetics that really shows that you're designing a good API. It's aligned with the conventions of these other APIs and all the kind of institutional knowledge that led to that semantic representation. So pretty happy with it. Now, this is the first time I've actually talked about API design in a long time, because most of this is not about implementation. You look at this stuff, it's like this doesn't do anything particularly interesting, just some information. Struct does like a little bit of reflection stuff, but again, it's just sort of trying to make sure everything lines up and you're getting things represented in a generic way that you can also sort of extend and create new types, new field types. I love it. I'm really happy with this. Decisions like this where you have, it's based on a single value and doing bit masks, but then you never really have to use them because you can just list them out as variadic arguments here. And then when you want to know, you can use these helper functions and they'll do the bitwise logic that I always forget. I'm pretty sure this is right. I think I wrote a test for it. But yeah, I always wanted to talk more about API design at some point, but one, I had not, to me, API design and developer experience are kind of the same thing to me. Your API is the user experience. It is the interface design of software from a programmer standpoint. And to me, that is the user of the future, is the programmer. So we need good APIs. API design is important. And Go is one of the only places that really, really thinks about it from a systemic point of view, not just the API and how the API is designed well in the same way that like Twilio thinks about API and the REST API and how it's designed well, But Go is like much more holistic. They're like, well, the implementation is important too. That needs to be as simple as possible and needs to be aligned with the API, right? It's not like that hard abstraction where you're like, design a nice API and then you implement it however you want, right? Because that doesn't necessarily, in the end, the user has to develop a mental model of how it works. And so the simpler you can design the implementation and align it with the semantics of your API, the easier it will be to understand and use and reason about. And that's the most talking I've done in weeks. But yeah, these are great examples of API design. Especially because a lot of what both of these things are about is trying to take advantage of the functional utility of good design, of using Go interfaces, stuff like that. I wish there was a lot more content like that in the world, because it's fairly hard to come by. It's a little bit more, Kenneth Rees talks about designing for humans in the Python community. I think DevX is sort of still a nascent field or discipline or way of thinking. That is not very well known. But like Go, the Go developers are some of the only ones that really show the thought that comes through in their APIs. So a lot of the best API design stuff I've gotten from Go, which is weird because it's specific to Go, but you can extract a lot of great generalized API design knowledge from it and try and translate it to other platforms. But I don't know. I was going to try and do 2 streams today, one for Dabble, implementing this field stuff in it. And then one, I was going to switch gears entirely and go back to Mac schema, try and wrap that up. Mac Driver was one of the first big projects sort of put out this year to sort of kick things off. And I'd like to see that get closer to a 1.0. And that's missing code generation stuff, which is dependent on Mac schema. Mac schema is almost there, so in parallel, I finally have somebody helping me working on stuff. Matt's working on trying to solve some of the Mac driver, sort of figuring out how to do auto release pool stuff and memory management kind of stuff. Worrying about whether you need to retain or not. It's kind of unclear. So that's something that we need to figure out, have the tooling for, and then document it. But we kind of need to figure it out first. I've just been kind of shooting by the hip this whole time. I mean, at some point I could just transition this into more of a roadmap-y kind of thing. I'm trying to put together a tractor demo. It's actually going to be a private demo, but it's kind of going to show a lot of stuff. Things that you haven't seen in a long time. Things like this. Things like, some of all the weird stuff I was doing in Tractor Studio. I think there is a bunch of stuff in, Visgo, Where's that? All this kind of UI stuff. Visgo, that was a long time ago. Right, we can come back to this. Right, imagine being able to visually write Go, visually read Go. Visually read Go that then compiles into a Mac application. So yeah, Mac driver. Somebody pointed out, I'm surprised they even were looking at it, but we found out that this was a bad URL, so we fixed it. Thank you for that issue. But Macbridge is another spin out from MacDriver, and so that's this declarative style API. It's a little bit more complicated, but it's a subset of the APIs, because there's sort of a trade-off of, like, if you're going to do a Electron alternative, it's based on a lot of common APIs, so things like creating windows and creating menu items and stuff like that. But of course, that's a subset of what you can do on any particular platform. So cross-platform will always be a subset. But I always want the ability to go in and actually do more things with the platform, especially because there's a lot of cool things you can do in iOS stuff, because frameworks, delegates, I mean, it was designed with a concept of object-oriented programming that really got the idea of like extensibility and, you know, some of the ideals of like Smalltalk. People just don't appreciate these days with Swift and shit. Although Swift UI is nice, but the idea is we don't need it. So yeah, having those low-level APIs. I've actually also been experimenting with Go Mobile to try and actually see. For a long time, the idea was maybe you could use this to write iOS apps. I'd love to write something in Go that would run on my watch, my Apple Watch. So I started stepping in that direction. I started playing with Go Mobile, which is a semi-official, loosely whatever, you know, the X repos, way to build applications for mobile, which basically means iOS and Android. And it does a couple of things. It has some things I don't care about. It actually has a bunch of, basically has a library or a framework to do things cross-platform, which I don't love. You get to it. Yeah, we're in command. We want to go to mobile. Yeah, there we go. So it's got a bunch of stuff. This app thing, it's like, oh, you know, it seems to focus on like events. So it's like, here's an event loop. So you can handle application lifecycle and mouse events and touching and redrawing and all that shit in a cross-platform way. But it's like not really, one, I don't want to do this. This is not how I think about building apps in either situation, really. Even though it's fine, there's nothing wrong with it. So this doesn't really get me much, you know? And then it turns out, you know, the real thing that I wanted was the commands that it uses to do the build. It has two command line tools to basically wrap Go build to basically produce a even signed binary that you could then just drop onto an iOS simulator or drop onto your iPhone in Xcode. And I got some of these examples to work. Here's like, yeah, it draws a triangle. Flappy is, I don't know if there's a screenshot, but it's basically like a Flappy Bird, but with a gopher. So it's a graphic application with some sprites. I got it on my phone, but it kept crashing. And I don't know if that crashing was because it's like missing some entitlement, like if it was not built properly, or if those are just like buggy game code and it was getting some like nil errors or something. It's not very clear. I was gonna try and get my friend Chad to help me debug iOS apps, only he doesn't have experience with Go, and I'm using this kind of level of indirection, but hopefully I can kind of find out. But it kind of worked, but it also kind of didn't. And then so I decided to go in and figure out, well, what the hell is it doing to build this stuff? And you know, it's just doing a bunch of stuff that it basically has like a templated Xcode project that it sets up and then puts files in, and then, you know, does some Xcode run commands. Like, in a way, like I even had to hack this because it hard coded the certificate name here, and there's been a pull request or a CL or whatever for like over a year to parameterize this, and it hasn't gotten in. And it's like I couldn't compile because I didn't have my certificate as a developer, Apple developer certificate, not an iPhone developer certificate. So this didn't even work. I had to just like edit this code in my local instance. But it's like, well, if I'm doing that and all this thing is doing is wrapping some commands and stuff, like I could do this. So I'm realizing Go Mobile is maybe going to be a great reference for me, but I don't think I'm actually going to use it. And so I'll have less software to blame when things aren't working. But I think if I were to get that working, using MacDriver with it will just work. Because as far as everything I've seen, yeah, I don't know. I don't know where I'll put that or where it will live, but it will be a great complement to MacDriver. And then in theory, yes, I should actually be able to make iOS apps and Apple Watch OS apps or whatever in Go. And if you have a visual programming language, you can visually make them. What else? Recently was talking about, you know, you release QMux. QTalk is a suite that's been around. It's mostly just QMux and QRPC. At some point I was going to write an article kind of explaining the design of that whole stack. But I also got a bunch of interesting ideas for other layers that might be interesting that I want to explore. But those can come after QRPC is released. That means I might want to put off writing this big article on all this, those design decisions. Just like put out QRPC. Re-aggregating them into a single QRPC project will maybe make sense once there's like a third project, but I've aggregated and disaggregated those projects with almost every rewrite or every iteration. They're not rewrites. But I'm glad that there's some like final public releases of these. I'm actually, this is still, there's still no actual release for this yet, although it's useful, but I just wanted to finish some stuff up in the TypeScript implementation. And then I was going to do a blog post on building Grok Tunnel, kind of explaining this this really short demo. It's really cool. And then Qmux feeds into the Macbridge stuff because it's used for Macbridge. And in thinking about it, because this is sort of like prototyping what that cross-platform API is going to look like, and I had this idea that, oh, I'm going to have to do a Win driver and a Tux driver, and then those bridges, but because there's actually some pretty good Windows Go bridges out there, there might be enough to do the basic resources I want to do here. Probably the same with Linux. And so ultimately that would be like Mac driver, Macbridge, WinBridge, TuxBridge. But at that point, they might as well be all part of the same cross-platform thing. So I think that project's going to be called Shell Driver. And I think I might even just rename Macbridge to be Shell Driver and put all the stuff specific to Mac OS under a Mac OS directory. And so that'll kind of be the start of cross-platform stuff, because once there's a cross-platform Macbridge, then everything I make will be cross-platform. So all the stuff I've already made, like Top Frame and whatever, I can start releasing Windows and Linux versions of those. Tractor Studio, all of that stuff. There's actually a bunch of stuff to do in Tractor and Tractor Studio that I kind of left, hanging at the end of last year, and also coming back to VisGo. So now that like the Mac driver and Shell driver roadmap pipeline is in place, is moving forward. And same with the QTalk stuff, Qmux and QRPC. And I'm getting close with having another demo application based on the Airtable clone. Things are going well, and I can start getting back to some of the more further down stuff. That is more visually interesting, that is kind of higher level than all of this stuff. Like I've been in low level stuff for basically this whole year so far. I get back to doing UI and Tractor Studio and making weird applications in that framework. While also having a, well, I'll talk about that another time, but basically, all of this now needs to be kind of refactored with and I was kind of waiting for this to happen. Like I didn't want to come back to this until I had a solution to the manifold APIs and the field stuff. So having both now, I can come back and start doing Tractor Studio stuff after some rewriting, reintegration stuff. But so if you're a sponsor, you'll probably get a private preview of all the cool stuff. I'm intentionally obscuring just how cool this stuff is working together. And it'll be in a demo, and my sponsors will be able to see that. And eventually that'll be a public demo. But by then I'll have other cool stuff in a private demo, so. Things are moving forward. And also, in I guess the next month or so, I'm probably going to do a big post. It's kind of almost recapping a lot of what I did here in terms of projects, like what I've done this year in terms of, Mac driver, how that's going, all those projects, how they're going to come together. Qmux, QTalk, QRPC, all of that. And all the interesting demos that I've been trying to make along the way. Anyway, I'm gonna have to take a break before I come back to actually work on anything. There is a slight chance I will not come back today, but I have a lot of energy. This is all very energizing, so I would like to come back to it and actually get some work done on stream, hopefully, ideally. And so that will probably be my Dabble clone, so. I'm gonna shut down for now and hopefully I'll be back in an hour or so. Yeah, I might eat, and then I will have energy. This is definitely one of those streams that was made for the VOD, so for everybody that's watching on VODs, this one's for you. I'm actually glad too that I've noticed that people are watching the VODs, because then I don't feel so bad talking to the two lurkers that are in here or whatever. Because I do need to get this stuff out of my head. Man, a 2-hour-long recap video. Change the title. Didn't really get anything done on Dabble. This is recap. Well, there's a lot about fields. Faceted data structures. API design talk. Yeah, I'll figure out some kind of title for this. Also kind of like that I was able to show like my notes and the thought process in doing the fields package, for example. And Faceted, kind of showing the original or a recent iteration of the manifold API and, you know, the problems there. Recapping on kind of Go interface polymorphism and extensions and stuff, and how that all you can kind of see influence the design of first the CDS composable data structure failed experiment, and then faceted data structure, which is pretty cool. I sent a link to Brad Fitzpatrick. He's like one of the only Go people I know that I kind of trust his design sense to be at least Go idiomatic. But I didn't get a response, so. A couple people commented on the gist. Mostly kind of wanting to see how it would compare to doing it normally, which I tried to do in this video, but it does, with no context, it really doesn't seem like probably people would ask, what would this be for? Because it's more than just the faceted stuff, the kind of ECS influence, but it's also then using that with interface polymorphism. Anyway, I've already talked about it, so done. Goodbye.